So now we're going to circle back around to a part of electric field that we discussed at the beginning. We sort of danced around it a little bit, but now we'll formalize it. We said that a source charge makes an electric field that fills up all of space. So a good thing to be able to do is to map that electric field. What does it look like everywhere? To do that, we draw what we call electric field lines. They map the electric field in space around a source charge. So let's say we have a source charge. Let's call it positive, so it's plus Q. What does the electric field look like everywhere? Well, to think about that, let's ask what would happen if I placed a positive test charge at this little black dot? Well, that little positive test charge would be repelled by my positive source charge, and it would move away from it. So my electric field vector at this spot points away. And I can do that at other places. What if I do it out here? It'll still be repelled, but not quite as strongly. So the electric field out here is weaker. And I can do this at any spot I want to. So I can pick a whole bunch of spots randomly, and I could draw a whole bunch of these little electric field vectors everywhere. Well, if I did it everywhere, I would end up with a map that looked like this. So my electric field lines would radiate outwards from that positive charge, and they would just keep going if I have my positive charge here all by itself. Let's write down some details about this. Let's see, if we're very far away from our source charge, the electric field is weak. So out here, the field is weak. What we might notice here is that the electric field lines are far apart. So that's one feature of electric field lines. The electric field is weak where the lines are far apart. If we're in close to the charge, the electric field is strong. That's where the field lines are close together. And why don't we finish things by writing down our expression for electric field? The magnitude of the electric field is K times the magnitude of the charge divided by how far away from you are the charge squared. The direction of an electric field vector is away from a positive charge and toward a negative charge. Let's see, and you might notice here that our electric field lines never ever cross. And that makes sense because it would mean that the electric field vector has two directions at the same time, which is not physically realistic. If you wanted to use an online simulation to draw these field lines, you certainly can. The PhET simulations are super for modeling these electric fields. If you type PhET electric field into your Google search bar, you should get a hit. Click on your first hit, and that says simulation of electric fields. Click play. You wait for it to open, and then all you have to do is drag in your positive charge. It shows the electric field everywhere around that positive. Where the lines, the arrows are bright, it's where the electric field is strong. Where the arrows are dim, it's where the electric field is weak, and it shows that the electric field is radially outwards. You can use this simulation to map the electric fields of any configuration of charge, and I would invite you to open up the simulation and have a look at it and see how it works. We can also draw our electric field lines around negative charges. So if we pick a point in space, the direction of the electric field is the same as the direction that a positive test charge would move, which would be in towards a negative charge. You can pick these points anywhere. If we're far away, the electric field is weak because we know that the magnitude of the electric field is K times the magnitude of the charge divided by R squared. And for this problem, we know that the electric field points towards the charge because our charge is negative. So we can continue to draw little arrows. at all the different points in space. And then what we would find, if we drew a map of all of those arrows, the net electric field would look more or less like what it did for the positive charge, but all of the field lines would point in towards our negative charge. So another way to think about our electric field lines now is that our electric field lines can always start on a positive charge and go out from the positive, and they can always finish at a negative electric charge, so they can go in towards the negative and stop there. We can also do this one on a PhET simulation, and we'll look at that next. So here's our PhET simulation of the negative charge. I just drop in the negative, just set it up. There we go. We see that the electric field map, or the electric field lines around the negative charge, exhibit the same behavior as it did around the positive point charge. The electric field is strong when we're in close to the charge and the field lines are close together. The electric field is weak when we're out far away from the charge and the lines are far apart, and the electric field lines never ever cross. Let's map something just a little more complex. Let's find the electric field lines around a dipole. Now, a dipole is nothing special. These are two equal and opposite charges with a small separation. So if we want to map the electric field lines, we have to remember some things about electric field lines. They go out of positive into negative. So the lines are close where the field is strong. And they never cross. And another part that goes along with the lines being close where the electric field is strong is that the number of lines is proportional to the size of the charge. So a big charge would have a bigger electric field. Those lines would have to be closer together, and that means there would be more lines. We're not going to see that exact thing in this example, but what we will see in this example is that the two charges have the same size, so they'll have the same number of electric field lines. So our electric field lines will have to come out of the positive and go into the negative. There's one line. Then we'll draw another line. That guy is going to curve from here to here. So we see that we have exactly the same number of lines coming out of the positive and going into the negative. The field is a little stronger in close to the charges and a little weaker further away. We can model this using our PhET simulation too. We can use our PhET simulation to map the electric field of the dipole. So I'll just hit play here. We'll put in the positive charge first. Make sure I get that in just the right spot. Then I'll put in my negative charge. And we see the same form as what we sketched on the previous page. We get lines going from positive to negative. We get some curving up here. And we have equal strengths around the positive as we do around the negative because they have the same magnitudes of charge. After we do our PhET simulation, we can return to our drawing and try and flesh it out a bit, just to add some details we might not have had in our original picture. So we'll add in that our electric field goes from the positive to the negative, kind of curves up around a little bit, getting the same number of lines out of the positive as we get going into the negative. But we can add on some other things too. Electric field lines don't necessarily just have to stop at a negative. They can also go all the way on out to infinity. So we can add those here on the side. They don't only have to start at a positive. They can also start at infinity. So now this is a nice complete picture of the electric field lines around a dipole. Okay, in this example, we have a negative and positive, but our negative charge is twice as big as our positive charge. So what this means in this picture is that our negative charge is going to have twice as many electric field lines. For every electric field line that comes out of the positive, we'll have to have two going into the negative. So here's one out of the positive, one into the negative. I need another one into the negative. That one is going to have to come from infinity. Okay, let's go again. One out of the positive, one into the negative. I need another one into the negative. That's going to have to come from out here. Let's do it again and again. So something like this. Then if we count our lines, we have 1, 2, 3, 4, 5 coming out of the positive. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 going into the negative. The negative charge is bigger, so the electric field is stronger because E is kq over r squared. The electric field is stronger, the lines have to be closer together, and that's what we see. Here, this charge is smaller, so the field is weaker, and the lines are further apart. We can do this simulation on PhET as well. So we just open up the PhET simulation. I'll put in my positive charge first. Then I'll put in two negatives. There's the first one. There's the second one. Okay, where the PhET simulation falls down a little bit is it doesn't draw the different numbers of lines. It indicates the strength with brightness. So if you look, you can see that it's stronger here around the negatives and weaker here around the positive because our negative charge is bigger. For homework now, as a project, you can use PhET to sketch the electric field lines for the following configuration of charge. I won't make videos for these, but I will post the solutions with the lecture notes. When we started discussing electric fields due to continuous charge distributions, we developed our idea by thinking about a long line of charge, even though we didn't go through the math of calculating what that field was. Let's use the PhET simulation to see what does the electric field around a long line of charge look like. So in this PhET one, this takes a few minutes to get going because you have to put in your charges and you have to make a line of charge. I would certainly invite you to do this for yourself. See if you can do a better job for me. I tend to be a little impatient, so I don't want to take the time to put in as many charges as I should. So this is a good process actually to model that idea of the fact that a continuous charge distribution is made up of a bunch of point charges. That's what you're doing here. You're putting in a whole bunch of point charges and you're making a line of charge. Okay, so there's our line of charge. And if you look at the electric field, let's not look up at the ends. Let's assume it's infinitely long. The electric field points straight away from it. And that was a result we saw when we did, when we talked about the symmetry. We saw that the y components canceled and we were only left with the x's. So that's what the electric field around a line of charge looks like. It points radially outwards. If we wanted to think about what the electric field of a capacitor looks like, and we did discuss this a little bit, let's go ahead and make a capacitor by imagining now that instead of this being a line of charge, it's a plane of charge. And let's put in a second line, this time it's negative, to complete our capacitor. So it is just a model. We're imagining here that these are planes instead of lines, but it is still good as a visualization tool. So what I'll do now is I'll put in enough negative charges so that I have about the same number of negatives as I do of positives, because remember that's what our capacitor is. It's two plates with equal and opposite charges. So our big takeaway here is that the electric field between the plates is constant and it does point from negative to positive as we discussed. If we were going to draw those electric field lines, let's just draw our line of charge here and I'll color it in. My electric field lines for my line of charge will go radially outwards in all directions. Okay, so I'm going to try my hand at three-dimensional drawing here. So it's not just left and right, it's also into the page and out of the page. And this will be a result we rely on when we come to talking about Gauss's law. So this is line of charge. E is radially out. If you think about the fact that your line of charge is a bunch of point charges all in a line, and that for a point charge, E is kq over r squared, E actually is weaker far away. So E depends on 1 over r. So it depends how far away you are for the strength of your electric field. Okay, so for our capacitor, we would have so this is a capacitor. We would have two plates of charge here, so we're imagining these are two-dimensional plates. They have equal and opposite charge, and the electric field is in the middle going from the positive to the negative. So E is constant and goes from positive to negative.